Not really. So I almost said, who are you? I didn't recognize you with glasses on. Oh. Okay, so put your stuff in your folders and bring your folders up to me, please. Please make sure everybody's name. Yes, very good. Paper clips right up there on that tray. Folks, can you bring up the folders? Okay, can we stop the chatter? Thank you. Okay, so today we're going to start section 1.6. Yay! This is, I think, the last section in chapter 1. No, maybe there's one more. But we're going to cover this over 2 days. There's a lot of other types of equations in section 1.6. So we'll cover most of it today, and then a little teeny piece on Monday, and then we'll go into more stuff. Don't forget, your last quiz on all of this material is next Wednesday. Your first test is Friday. So I will post quiz solutions on Moodle. Has anybody noticed that I've posted quiz solutions on Moodle so far? Like your quiz solutions to your first quiz are on our Moodle site. And I will post today, before I go home, quiz solutions to our second quiz, okay? So you can find quiz solutions on Moodle. Okay, so let's take a look at the first part of today's material. And you want to start us off, Brendan?
Polynomial equations other than linear and quadratic can sometimes be solved by factoring and using the zero product principle. Let's begin today's class by seeing how strategies we have used to solve linear and quadratic equations will help us solve the following fourth degree polynomial equation. X to the fourth plus x to the third equals 6.
And why did we call this a fourth degree polynomial again? Eric? The highest exponent is 4. So here I'm using language, polynomial equations. Your book will define for you what a polynomial is. But the nice thing about polynomials is the only type of exponents you see would be 0 or the positive integers. You will never have anything in the denominator, any variable expressions in the denominator. You will never have, that means you'll never have negative exponents, okay? So this is what we call a fourth degree polynomial equation. And you haven't seen how to solve these before, most likely. But this zero product principle that we use every time we factor to find the values of a denominator that equals 0, or when we factor a quadratic that's set equal to 0, can be used to help us out here. So let's start by taking a look at how we're going to deal with this particular equation. Okay? Set the equation equal to 0 by moving all non-zero terms to one side of the equation. So what are we going to subtract from both sides of the equation here? 6x squared, right? Now remember, I've got this in, you want to underline this. Never divide both sides of the equation by x squared. Does anybody know why we don't divide both sides of our equation by x squared? All right, let's suppose the 6 was not attached to it, and we just said, oh, I can make this easy by dividing that by x squared, that by x squared, and that by x squared, and then I'll get a little baby quadratic, which is easy to solve. So why am I suggesting that you never divide both sides by x squared or x to any power? Does anybody know? Yeah, Eric? Yeah, so what happens if we solve this equation and one of our solutions is 0? Well, you know what, it might be a little easier to see why we can't do this if we go ahead and solve the equation, and then we'll go back and look what would have happened if we divided by x squared. It might be easier to do. Okay, so let's take a look. This is now our equation. Once we subtract 6x squared from both sides, we now have our equation set equal to 0. Okay, so you look at this and you say, this is not quadratic. It's not linear. What's a student to do, right? You're sitting here a little puzzled. But again, I want to remind you, circle the highest exponent, because what does that tell you about the maximum number of solutions you could have for this equation? Does anybody remember the maximum number of solutions we could have for this equation, Julia? One less than the highest degree. That's possible. I think, let's see, so that would be 3. So the question is, could it be anything higher than that? So let's think about a regular equation. Let's think about a quadratic equation. Here's a quadratic equation. And let's see if Julia's idea works out. Okay, so what's the degree here is 2. Does anybody know how many solutions this would have? It would have 2 because it can be factored like this, set equal to 0. X could be -3 or -2. But you could also have, to just support what Julia is thinking, you could also have a quadratic equation like this, where you only get one solution because this left-hand side is a perfect square where your factors are identical. So you only have one solution. So sometimes when you look at an equation, you check out the degree. That's always the maximum number of real number solutions you could get. But you can get anything less than that. For a quadratic, you can get 2 solutions, 2 real number solutions, 1 real number solution like this situation, and sometimes you get no real number solutions because they're complex. So with this particular equation, even though you may have 3 solutions, maybe, the most number of solutions you could have is 4, okay? That's the maximum number. We may get less than 4, and we may get no real number solutions. We don't know until we solve it. But what I'm showing you here is just a little thing, a little habit that if you sort of get that into your your pathway, into your brain, it might help you so that if you're doing a quadratic, never mind, we talked about that the other day. All right, so we still have to figure out how to do this. If we're going to use our zero product principle, the word product suggests that you need to create some factors. You need to factor. So how am I going to factor this other than Brendan and Eric? Ian? I have a GCF here. And in fact, the greatest common factor is your best friend. Okay? Joe, do you mind shutting that door? Thank you. So the greatest common factor is x squared. So when you factor out the x squared, you have an x squared plus x minus 6 left inside. So now you have 2 factors. The question is, are both of those factors prime, or can they be factored further? So you check out x squared, you say, hey, x squared is prime. I could write it as x times x, but that doesn't do anything. And now you check out your second factor and say, hey, can I factor this any further? And what's our answer? X plus 3, x minus 2. So then I factor that. Okay. So notice you have 1, 2, and then x squared. Okay. No. Oh, when you said x squared equal to, potentially yes, if you had a constant other than 0, which I said on Wednesday, but those are the little things that kind of go by the wayside. So now you have 3 factors. I'm going to underline them in different colors. There are, oops, that was supposed to be black. And here's our blue factor. So you set each factor equal to 0. So I take out my first factor, x squared, and I set it equal to 0. Guess what? When I take the square root of both sides, I only get one answer because 0 is its own, right? Its own square. It doesn't have a plus and a minus. So there's one solution. So look what would have happened if we had divided up here by x squared at the beginning. We would have gotten this equation right here. We would have gotten that equation. We would have only had 2 factors instead of 3, and therefore we would have lost one of our solutions. We would have lost a solution to our equation if we had divided both sides by x squared. And on top of that, you would have been dividing both sides by 0, which we're not allowed to do. Okay, so you never want to divide both sides of your polynomial by any x to any power, ever. X to the first, x to the second, x to the third, because you're throwing away one of your solutions. Okay, let's take a look at our second. So we've set our first factor equal to 0. Now we have to set our second factor equal to 0 and solve that. Well, that's just a baby linear equation. And now we have to set our third factor equal to 0. So there are our three solutions: 0, -3, and 2. So our solution set, and if we were putting this in my math lab, how do we actually input the three solutions? Right, we have to put them in ascending order from smallest to largest. Okay, smallest to largest. Okay, so there's our solution set. And then you always want to go back and check the answers note in the original equation, not any equation that you've manipulated, because if you made a mistake, your answers are going to support your mistake. So go back to the original. I'm not going to take the time to do that. So our goal when we have polynomial equations is to try to turn our equation into the simplest possible. Notice we turned our equation into a little baby quadratic called x squared is 0, and then two linear equations, baby linear equations, so we knew how to solve it. But you never would have gotten here if you don't remember your greatest common friend. All right, your greatest common factor, that's the key. So when I say to take a pen and etch it on your palm, it is really the best little thing for you to remember, a little technique. Are there any questions on solving this polynomial equation before we move on? So let's go to the end for a minute. And I'd like you to do number 1. I'm really not going to talk. You're going to describe the steps for me one at a time. If one person gives me the first step, then someone else in the class takes over immediately. Okay, so I'm the writer, so Cecily, you want to start us off? Okay, so now she's all done, just like she's turned off at the bar. Okay, someone else. Just go ahead. I'm not going to call on anybody. I'm not talking to anyone.
X inside the parentheses, x squared minus 16. Close parentheses.
Okay? All right. So those are polynomial equations. Okay. So now let's take a look at, well, first of all, I want to show you the equation that we just did a minute ago when I was kind of harping a little bit on never dividing both sides of x squared because you lose a solution. Let me show you why that's critical. Because hopefully by the time you leave this class, you'll have a sense of what a graph would look like that was set if we set this equation x to the 4th plus x to the 3rd minus 6x squared equals y, and we were to graph that. Hopefully you'll have a sense of what the picture could be, one of the pictures. So let's take out our graphing calculators now and see what is the relationship between these three solutions, 0, -3, and 2. Where do those appear on our graph? So think about it. These values for x are making y equal to 0. What are those called, those points? Where y equals 0? X-intercepts, right. So these create 3 x-intercepts, because these are the values of x that make y 0. So you should expect that when you graph this equation, x to the 4th plus x cubed minus 6x squared equals y, your graph is going to cross your x-axis in 3 different places. So let's take a look at that. So I'm going to call up my handy dandy calculator. You call up yours. So we're going to set this equation equal to 0. I got to turn it on first. Okay, so we're going to set the equation equal to 0. I'm going to clear out whatever's in there. So let's see, it's x cubed, x raised to the 3rd power, plus x squared, take away 4x, take away 4. I'm going to start off with my standard window. I've never graphed this before. I don't know if my standard window is appropriate, but it may be, and I'll be fine. So I'm just going to go down and say standard, and then it starts to graph. Nice. So do I really need to go out as far as -10 and +10? I kind of want to see this a little clearer. So now I'm going to, well, I could take a picture of that if I want, but I want to just make this go, say, from -5 to +5, because I want to be able to see where it crosses the x-axis a little clearer. So I just changed my window. Instead of it going from -10 to 10, I made it go -5 to 5, and that way I sort of zoomed in a little bit. So let's take a picture of this. You can draw this on your own at your seats. Draw a replica of this. Okay, and we'll put this right in here. All right. Now notice the x values of our x-intercepts, right? The x values of our x-intercepts. So it's right here. It's -2, 0, -1, 0, and 2, 0. Okay, is that what we got a minute ago for our x-intercepts? No, what did I, oh, it's a different equation, right? Okay, so it's a different equation. It's not the one I did in number 1. Okay, so, but these are our x-intercepts. You might say, how could I find those on my calculator if they weren't really nice, rational x-intercepts like 2, -1, and -3? Well, you just do second calc, and you say, go down to 0. That's the key command, 0, because you're saying, when is y equal to 0? So that's the command you want to use. So I'm going to put this right over here. You hit 0. And notice you've got 3 different spots on your graph. So look, it says, go to the left of your first 0. Here's my first 0. It's at -2, right? So do I have to really move my cursor so it's to the left? No, you could just enter a value if you want to, like -4 is to the left of that. So I'm just going to put in -4, and I'm going to hit enter. And now I hit a value to the right of here, but be careful. You don't want to go a number way over here, because then you're going to go straight through this 0. So what's a number between -1 and -2? Any number between -1 and -2? -1.5. So let's put that in, -1.5. And now you say, guess. I'm going to let the calculator guess, so I'm just going to hit enter. And voila, there's your first 0. There it is, -2, 0. So x equals -2, y equals 0. So let's try to use our calculator to find the next x-intercept. So let's take a little picture of that so you have it at home for later. So we're going to take a picture of that. All right. So let's see if we can remember the steps together. Okay. So I want to find my next x-intercept. Where is it? It's right here at -1. So I want to pick a number just to the left of it, but I don't want to go past this one. So I'm going to use that -1.5 again. Okay, but to get there, I say, go to my calc menu right here, go down to 0, because this is called, we're calling them the x-intercepts. And in a little bit, we're going to be calling them the zeros of the function, but we haven't covered functions yet, but that's where we're going. So that's why they use this term zero here instead of x-intercept, but it's the same thing. So you could make a note saying, when I see zero on my calculator, that's the same thing as what I've been calling x-intercepts for years, okay? So now we're going to hit enter, and now we're going to go a little bit to the left of this one, right here. So I'm going to enter negative 1.5. I'm not going to play with my cursor on the curve because this is much easier. And now I go anywhere to the right, as long as I don't go past this number. So conveniently to the right of that is 0. So I'm going to enter a 0. And then I hit enter, and it's going to say guess. And every time it says guess, you can say freebie, hit enter. And there is negative 1, 0, which is our other x-intercept. That's cool. Okay, so now use your graphing calculators to see, even though we know what the answer is, 2, 0, see if you can come up, use the steps that we just outlined, to come up with 2, 0 on your graphing calculator. So here's our second x-intercept. Okay, so use your calculators now, and while you're doing that, okay, so we know that if we work through this, our last picture would be 2, 0. So I'm not going to take the time to do it unless you need me to do it. If you do, I'll do it. Does anybody need me to do it? No? All right. Okay, so our final one is x equals 2, comma, y equals 0. And we can see that right there. Okay? Now, folks, these x-intercepts, negative 2, negative 1, 2, represent the solutions to this equation. Why? Why do they represent the solutions to this equation, Brendan?
Because when you solve the equation, we set y equals 0.
Right, so when we solve this equation, we move all our terms onto one side. This is our particular way we're doing it now. We're putting all of our terms on one side of the equation, we're setting it equal to 0, and we're saying, what values of x make this equation 0? Those are our x-intercepts. Therefore, our x-intercepts have a dual purpose. They're not only x-intercepts for the graph, but they also tell us the solution set, okay? So our solution set here would be in order, negative 2, negative 1, 2. And that's how we write it in my math lab, okay? Now, that's not the method we learned earlier. The method we learned earlier said, okay, so I want you to have this. This was back in class 5. Another way, so we know this is our solution set right here. We learned another way to find the solutions to that particular equation. Oops, it looks like I have 2 different solutions in here. Sorry. This should be typo, 4x plus 4. So write that in. That's the one we're solving. Okay, so back in class 5, when we were learning how to use our graphing calculator, we didn't put everything over to one side and look for zeros. What we did is we said, let's take the left-hand side of our equation and put it into y1, and let's take the right-hand side of our equation and pluck it into y2. Right, so let's try that. It's a little different method, a little different idea, but you can use either one that makes the most sense to you. So x cubed plus x squared, and then on the y2 is going to be 4x plus 4, okay? And now we hit zoom standard and graph to locate the x value of the intersection point. So now what we're going to do is we're not interested in where this crosses the x-axis anymore because our equation is not set equal to 0. We're saying, when does this equal that? So we want to find our intersection point. So I don't know why I put zoom standard in. Well, we'll do that in. Okay, so there it is. There's the graph. Okay, but can you see the x value where? No, it's all squished in here, right? You can't see it, right? You can't see where those two are intersecting. And it may be more than one spot where they intersect, right? You can't even see above, right? So let's zoom in a little bit, see if that helps. Zoom in. Zoom in a little more. There we go. So now can you see one spot where it crosses, where the two intersect right here? At -2, right? It intersects at -2, but let's suppose it was a funky number like negative 2.145678, right? So you use second calc and you say, where do they intersect? And you say first curve, you can kind of bring it over if you want, close on the first curve, and you say, okay, that's close to where they intersect, enter. Second curve, I'll just get it close, enter, enter. And there's your negative 1, 0. Okay, yep. Oh, right. So I put a whole different equation. Okay, hang on. What? Remember I told you I did these this summer and that I would find typos? Okay, it's supposed to be this equation here. All right. So this should be, and I apologize, people. This equation here should be x to the third plus x squared equals 4x plus 4. Okay? So just cross out that equation because we're trying to look at this. We just did this equation a minute ago and found the solution set, right? Now, if Julia hadn't told me that, I would have found out I made an error because when I went to look for these other two solutions, they wouldn't have been where these graphs intersected, and I would have gone, what? And then you would have helped me, hopefully. Okay, so let's go back. Let's go back.
You have it correct. That is correct.
So, of the previous one?
Yeah.
Oh, okay. Here it is, 4x cubed plus x squared equals 4x plus 4.
That's what it should look like. You just have to further up the screen.
Okay, so we just found negative 1, right, as a place where they intersect, right, folks? We found negative 1 right here is where they intersect. So how many intersection points? Right now, with this view, how many intersection points can we see? We can only see 1, but we know it's got to intersect how many times? 3. So you have to play around with your window. So look, we've got 1. We know they intersect x equals negative 1. Look, folks, see right here at negative 2? If you come down, you're going to be able to see another intersection point, but not with this window. So you've got to manipulate your window. Here's the one time it's okay to be little manipulators. Let's try negative 5 to positive 5, and let's see if we can see where it intersects. Okay, so there we go. Oops, do we have a low enough value for y yet? Nope. So now we've got to just mess around with the y. Let's say negative 8 to positive 8, and let's make y negative 8 to 8. Okay, and let's try that. I just want to be able to see where they intersect, so I'm just stretching out my y. Ooh, can I see it now where they intersect? Yep. So now I say second calc. Where are these two curves intersecting? I go down to intersect. I hit my enter button. And then I say, okay, let me go on to my first curve and kind of get in the general vicinity. Yeah, that's in the general vicinity. Let me pop over to my second curve. I'm going to hit enter, enter. And there's my negative 2. Okay? Now notice y isn't 0 here because we haven't set our equation equal to 0. So at x equals negative 2, the left-hand side of my equation and the right-hand side equal negative 4. And one more time and you'll get your answer of 2. Okay? So those are two different ways to find the same answers. So what I want you to do now, you notice I have this little pad with a pencil, is I want you to briefly write down the ideas that you used in each of these two graphing methods, and then state what your preference would be. So if I gave you an equation, first of all, what are the two ways you could find the solutions? We just saw two different ways, and then write down what your preference is. So take about the next type of equation we have to solve. Your friends, the radicals, are back, okay? And so when we look at a radical equation, the first thing you have to do is to be able to identify it as different than the one we just did. And it's pretty, I hope, like knocks you right in the face because you see a radical symbol, right? So We're going to start the same way we always do, with the idea that we use to solve any equation is, in this case, you have an x term here and you have a square root of x here, right? So you want to isolate. You want to get all by itself your radical term on one side of your equation. That's your goal. So how are we going to isolate? We're going to isolate the square root of x. We're going to isolate the radical term. That's the language we use. It's a term. Because if you haven't had this language before, anything that's separated by a plus or a minus is called a term. Okay, so these are terms. This is an important vocabulary word to have down. It's used all the time. Combine like terms, isolate terms, move one constant term from one side to the other. Okay. And so what are we going to subtract from both sides of this equation, Orlando? X. So we're going to subtract x from both sides. So let's do that. And our resulting equation has the square root of x on the left side and 12 minus x on the right side. So we've done our first duty. We've isolated the variable term. Now, to get to x, we have to undo the square root. What's the inverse operation of undoing the square root? Squaring. So we've got to square both sides of the equation. So in order to square both sides, okay, you just go in on the left. Excuse me? Yes, that's exactly what I was going to say, Liza. You're reading my mind. The right-hand side of the equation has two terms, so put your arms around it before you square it. Okay. Now, do you notice that I've been giving you binomials to square all the time? Some of you still haven't gotten that down, but hopefully you will. Be careful not to fall into temptation here. What's the temptation? On the right-hand side, when you square this, what's the temptation? You square, what'd you say? Yeah, the temptation is to confuse when you use your exponent rule, which is when you have a multiplication or division problem, right? This is subtraction. So it's not 12 squared plus x squared. That is not the answer. Remember, it's 12 minus x times 12 minus x, and the only way to do that is to what? FOIL, right. So on the left-hand side, the squaring will knock out the square root, and we're left with baby x, which is what we're hoping for. And on the right-hand side, we have to use FOIL, and so we're going to get 144 minus 24x plus x squared. Okay.
Isn't the x
No, you're undoing a square root. It just gives you x. You'll find out if x is positive or negative when you solve it. Okay? Now, what type of equation do we have right here? A trinomial is on this side, Orlando. That's okay. That's good. Trinomial is on this side. And remember, a trinomial, folks, is just an expression, right? So we got a trinomial on this side and a monomial on this side. But what type of equation do we have? Quadratic. And how do we know it's quadratic?
squared?
It says the highest power is a square. We call that second degree equation, right? So again, more language. We have a quadratic because we have a second degree equation. I'm going to turn you into mathematics communicators before you leave the class. So we've got to set our quadratic equal to 0, and we're going to do that by subtracting 1x from both sides. And on the left side, we get a 0. And on the right side, we have 144 minus 25x plus x squared. Now, we usually put our quadratic equation in descending order with your highest degree term first. So I'm just going to rewrite this and put it in descending order. So the question is, can you factor this? Do you know factors of 144 that add up to 25 off of the top of your head? You may or you may not. No? Okay. Factors, well, 12 and 12 add up to 24, right? So that doesn't work. Do you know any other factors that you come up? 11 and what? 11 and 14. Is 11 times 14 equal to 144? No, 11 times 14 is 145, right? 155, right? 150. No, it's 154. I got to show you the trick for multiplying by 11 someday when we have time. Remind me, even though I just did. So you're not quite clear whether you can factor this or not. So you can always rely on Kyle. X equals negative b plus or minus the square root. Okay, so a equals 1, b equals negative 25, c equals 144. So x equals. Now, if we solve this equation and we get rational number solutions, we could have factored it, but we'll wait and see. X equals, the opposite of negative 25 is positive 25 plus or minus the square root of b squared. Since b is negative, it must go in parentheses. Minus 4 times a times c. And it's convenient that that little line is right there for my fraction bar. Over 2 times a, which is just 2. Okay, so x equals 25 plus or minus. Negative 25 times negative 25 is 625. Minus, now 4 times 144. Bless you. I don't know that off the top of my head. So let me, 4 times 144 is 576. All over 2. Okay, and I'm going to just make that radical sign a little bit smaller. Okay. Now we subtract 625, take away 576. Ooh, it's a 49. Oops. Is that right? 49? Okay. So x equals 25 plus or minus the square root of 49 all over 2. Oh, this is turning out to be nice because it's a perfect square underneath there. Okay. So we get x equals 25 plus 7, because the square root of 49 is 7, all over 2. And we get x equals 25 minus 7 all over 2. So let's simplify that. 25 and 7 is 32 over 2. We get 16. And 25 minus 7 is 18 over 2, 9. So could we have factored this? We could have gone right back here and we could have factored this to be x minus 16 times x minus 9 equals 0. And we would have gotten our answers like that. So you could have played around with some factors of 144 for just a couple of minutes. And you probably could have saved yourself a lot of calculations. Okay. Now, anytime you square, folks, when you square an equation, you can always introduce, because your original equation, getting back to what Brendan was saying, was like, well, what about the absolute value? Sometimes by squaring, you're introducing an extra solution that will not work back in your original equation. So anytime you raise both sides of an equation to a power, you've got to remember this idea that you can have an extra solution. Okay, so you've got to go back and check. So let's put these answers, 16 and 9, back into our original equation and check them out. So our original equation, let's put the 16 in first. 16 plus the square root of 16 equals 12. Is 16 plus 4 equal to 12? No. So 16 is what we call extraneous. It happened because we squared both sides. We introduced a new. So you got to remember to do this, because guess what? That is not a solution. The only solution here is 9. Okay? And let's go back and check it instead of taking my word for it. So 9 plus the square root of 9, does that equal 12? 9 plus 3 Yes, that equals 12. You're happy, and that's your solution. All right. So I got one more type of equation to show you, and then I'm going to leave you on your own to do the exercises I've given you at the end of the section. So the last type of equation we have is an equation with a rational exponent in it. All right. We could rewrite this if we wanted to as a radical, if you want in radical form. But let's see how we would take a look at this without changing everything to a radical. So the first step is what it always is we want to isolate our term with the rational exponent. Again, what is term? Here's the first term. There's a subtraction. There's our second term. So we want to isolate our term with the rational exponent in it. Okay? The rational exponent. All right. So what are going to be my steps to do that? What will I do first, Orlando? It's right there. It's already on the left side, so I'm just going to keep it there. But I want it all by itself on one side of the equation.
Oh, so you just add 6.
Add 6 to both sides. Okay. Add 6 to both sides. And now I have 3x to the 3/4 equals 6. Okay. Isolating it means you have what for a coefficient? What number? When you isolate something, it's all by its lonesome. It's all by its onesome. What's the coefficient? 1. So you want to make sure you have 1 as a coefficient. So other than Orlando, Brendan, Eric, what would I have to do now so I just get x to the 3/4? What would I have to do to both sides? Karis? Just to make 3 into a 1? No, I can't get rid of that. I can never change the exponent, ever. I can never change the exponent. Okay? I want a 1 in front, Karis. So what would I do to get a 1 here? Karis? Divide by 3, yeah. Okay, and that's a mistake some of you made, and this is really good. I'm glad that Karis mentioned this because it's a really good reminder. When I asked you to evaluate on that first quiz, I think it was like 16 to the negative 3/2 or whatever, some of you flipped the exponent and made it 2/3. It completely changed the problem. You don't have any right to change the exponent. Okay, just remember that. It will help you when you're trying to solve some of these, evaluate some of these expressions. Okay, so now you get x equals 3, x to the 3/4 equals 2. All right. Now this is where I'm going to diverge a little bit and show you two methods. Method 1, method 2. Oops. Method 1 and method 2. Okay, so let's take a look at method 1. Method 1 is what I have all this language on the right-hand side for. So we have x to the 3/4 equals 2. Our goal is to get x equals some number, right? That's always been our goal. Find x, dude, right? So we want x to the first power. So any ideas what we can raise both sides of this equation to get x to the first? Now, Karis, is your turn. What can we raise both sides to? 4/3, because 4/3 is the reciprocal of 3/4, and when I multiply a number by its reciprocal, 3/4 times 4/3, those are reciprocals. What number, magic number, do I get? 1. Yeah. So this becomes 1, which is lovely because I get x to the first, and this becomes 2 to the 4/3, and that means 2 to the 4th, which is 16, and the cube root is 16. We can't simplify, so you can leave it just like that. You can leave it just like that. Right? But for some reason, students don't like this, like raising both sides to the reciprocal of the power. It's hard to get students to do that. And so what do? They fall back into method 2, where they do this. They take this and they put it in radical form like this. And this is okay. You're going to get the same answer. They put it in radical form and they say, okay, now I've got to undo the 4th root. When I had to undo a square root, I squared both sides. How am I going to undo a fourth root? Raise both sides to what power? Fourth, right. So I raise both sides to the fourth power. The 4 and the fourth root undo each other, and I get x cubed is 2 to the fourth. Notice, we're halfway home. There's 2 to the fourth. And now to undo x cubed, I've got to take the cubed root of both sides. So this is what some students like to do better. And you can either write it in exponent form or you can keep it in radical form like this. It's totally up to you. Okay? They're both the same. One isn't any better than the other. One's a little more archaic than the other, but so what? I'm a little archaic myself, right? So you now have lots of problems to try, and you've got 15 minutes of class time. I'm going to get out the flag, so if you have any questions, I can help you out.